We're now here, and we'll reach the autumn equinox point in 6 weeks. The Earth revolves around the Sun, but on an ellipse, not a circle. During the first days of July, we reach our furthest point from the Sun. So why is it so hot? In fact, the difference between near the Sun and far from the Sun isn't very great. There's a much more important variation. The Earth doesn't travel straight, but slightly askew. The Earth's axis is tilted. At this moment, the northern hemisphere is tilted towards the Sun. The days are long and the nights are short. But above all, because the Earth is tilted, the Sun's rays arrive at different angles. In winter, a ray of sunlight like this one reached us at a slant. Its energy was spread over a large area and we felt cold. Today, the same ray from the Sun strikes the ground from a higher angle. Its energy is concentrated on a smaller surface. We feel hot. In the northern hemisphere, it's summer. In the southern hemisphere, winter. We have seasons because the Earth's axis is tilted. The Earth travels on an elliptical orbit. But this ellipse is only 2% away from being a perfect circle. Is it possible to see such a small variation? Yes, if there's a total eclipse in July. Normally seen from the Earth, the Sun and Moon look the same size, although the Sun is really much bigger. By an extraordinary coincidence, the Sun 400 times wider than the Moon is also 400 times further away. So the Moon seems to be the same size as the Sun, covering it exactly. But in July, when the Earth is more distant, the Sun seems smaller than the Moon. If there's an eclipse, and at the same time the Moon is near the Earth, it more than covers the Sun. The shadow of the Moon is wider, and the Sun takes longer to emerge on the other side. These are the longest eclipses. On the 11th of July 1991, the Sun, at its furthest point from Earth, was hidden behind the Moon for almost 7 minutes. That was the eclipse of the century. The Sun seemed smaller than the Moon, showing the Earth was further from the Sun in summer. We're all affected by the eccentricity of our orbit. Like all the planets, the Earth travels faster on the part of its orbit near the Sun, and more slowly on the more distant part. In December and January, the Earth moved a little nearer the Sun and speeded up. Then, as it moved away from the Sun, the Earth slowed down like a train hauling up a slope. When the Sun is closer, its pull is stronger. So at the moment, the Earth is traveling more slowly and falling behind schedule. To cover the summer half of its orbit, it takes 6 days more than for the winter half. The spring equinox is on the 20th of March. The autumn equinox is on the 23rd of September, 3 days late. Look at your calendar. This summer half from March to August has 4 long months, with 31 days. While the winter half from September to February is shortened by February, which has only 28 days. That makes 3 more days. So we reach the autumn equinox point 6 days late. With the Earth circling at different speeds and our watches showing steady time, there are bound to be discrepancies. You can see them. Find marks near your house and note where the Sun sets on the horizon. On the winter solstice day, the Sun sets here. At the summer solstice, here. Each year, as the days grow longer, then shorter, the Sun makes a return trip. Each spring sunset corresponds to an autumn sunset. At the spring equinox, the Sun sets here at 8 p.m. At the autumn equinox, it sets in the same place at the same time. All well and good. But 40 days before and after the equinox, things are different. 40 days before the spring equinox in February, the sun sets here at 7 p.m. And 40 days after the autumn equinox in November, it again sets here in exactly the same place. But at the same time? No, half an hour earlier at 6:30. Why the same place and not the same time? Because in autumn, the Earth with its changing speed has fallen behind and our watches, keeping steady time, show we're ahead. Our cruising speed is 107,000 kilometers an hour. But at the moment, the Earth is moving more slowly. It's traveling at its furthest point from the Sun, and our speed is only 105,000 kilometers an hour. While in winter, when the Earth is accelerated by the Sun, we travel at 110,000 kilometers an hour. The difference isn't very big because our ellipse is almost a circle, out by barely 2%. On its more elliptical orbit, Halley's Comet accelerates to 200,000 kilometers an hour when it passes near the Sun, nearly twice the Earth's speed. Then, when it returns to the distant region of Neptune, it slows to 3,600 kilometers an hour, 30 times slower than the Earth. With such a narrow orbit, it's as if the Sun throws the comet out. Halfway, it slows down and falls back towards the Sun. If you throw a ball into the air, it rises on a narrow trajectory, slows, stops, and falls. The Earth is constantly falling towards the Sun, but don't panic. We're on an almost circular orbit, and centrifugal force keeps us firmly on our orbit.